Well, I hope you've looked at the equations and seen what we have to do. I wrote these out. Now let's look at these. First of all, we notice there are no x's in any of the y equations, so we don't even need to look at these. Let's look over here. First equation doesn't have an x in it. Remember, not the subscript x, but the variable x. No x in this equation. Here's an x, but we cannot solve this because we do not know v sub x and we do not know t. What about this one? Here's an x, but again, we do not know t, so we cannot solve for this one. This one has an x in it. Okay, so we have an x here. We don't know v sub x here. But notice, what is a sub x? A sub x is 0, and 0 times anything is just going to be 0, so that actually cancels out that x. It does tell us something interesting that we will use often. Notice, because a sub x is 0, 0 times x minus x naught is 0. What does that leave us with? Vx squared equals v naught x squared. We can take the square root of both sides of that, and what does that leave us with? Vx is plus or minus v naught x. So the final x velocity is positive or negative, plus or minus v naught x, the initial x velocity. Well, could it be negative? Well, we know in this case, because a sub x is 0, that's telling us that the x velocity does not change. There's no acceleration in the x motion. So that means that we could not end up with Vx equal to negative v naught x. So that tells us that Vx must be the same as v naught x. There is no acceleration in the x motion. That's something that might help us out sometime for some problem. So we could actually come over here and say, well, we do know what Vx is. Vx is the same as v naught x, which is 20 meters per second. There is no acceleration in the x direction, so the velocity in the x direction is constant. Okay, well, even given that, now what? We still cannot solve for x. Again, back through any of these, we could not solve for x, even though we now know v sub x here. We don't know t. We cannot solve for x because we don't know t. So what are we going to do? Well, this is a trick that we've got to keep in mind because it's something that pops up very often. If we knew t, we would be able to solve for x. Well, is there any way that we can solve for t? There is no way to solve for t in the x motion, but what about solving for t in the y motion? Can we come over to the y motion and find an equation that has a t in it where we know everything else? Well, let's look at the first one. Well, we can't solve this one. It's got a t in it, but we do not know v sub y. What about this one? Well, it's got a t in it, but again, we don't know v sub y. What about this one? Well, it's got a t in it, and we do know everything else. So we could actually use this third equation in y to solve for t, and then take the t over to the x motion and use it to solve for x. Okay, that's a possibility. What about the fourth equation? Well, there's no t in it, so we cannot use that. Well, there we go. That's what we'll do. That's how we'll proceed. We will solve this third equation for t, the third y equation, solve it for t, then we will move back to the x motion once we have t and use it to solve for x. There we go. Let's take our variables, let's stick all the values in that we know, and then we'll solve for t. So let's do that. Here I've stuck our values in. So for the equation y equals y naught plus v naught yt plus 1/2 ayt squared, y, we know all the values over here. Y is 0 equals y naught, 1.50 meters, plus v naught y, but v naught y is 0, so 0 times t is 0, plus 1/2 a sub y is negative 9.80 meters per second squared, times t squared. Multiplying that half by the negative 9.8 gives us a negative 4.90 meters per second squared. Taking this term, the negative term, and bringing it over to the other side, we have 4.90 meters per second squared, t squared, equals 1.50 meters. Dividing both sides by 4.90 meters per second squared, and we have t squared equals 1.50 meters divided by 4.90 meters per second squared, which is 0.306. Notice the meters over meters cancel. We have 1 over second squared, which brings it back up into the numerator, second squared. We take the square root of both sides, and that leaves us with t is equal to plus or minus 0.553 seconds. Now, we always need to think about this. Why do we have two possible results, and which one do we want? Which one actually satisfies the conditions of our problem? A negative time. First of all, what does a negative time mean? Remember back in the one-dimensional problems, negative times mean nothing more than times before t equals 0. Before our t equals 0, the initial time. Where's the initial time? The initial time is the time of our initial position. So it just means times before the ball was actually thrown. Remember, before the ball was thrown, what was it doing? Well, we don't know. Maybe it was in the person's pocket, Dr. Evil's pocket, or whatever. We have no idea about what happened to it before t equals 0. But the equations don't know that. The equations assume that the ball has been accelerating uniformly for all times. T after t equals 0 times before t equals 0. The equations assume that the motion has a uniform acceleration. Well, if the ball were accelerating uniformly before t equals 0, what would the motion have looked like? Well, to get to this position at t equals 0, it would have been moving up like this from over here, passing this point horizontally, and then continuing off down here. At a time of t equals negative 0.553 seconds, that's when the ball would have crossed the ground level back over here. Not during any physical part of the motion, but if we could imagine tracing a uniformly accelerated motion back before t equals 0 into negative times, that's where the ball would have been at y equals 0, which satisfies our conditions, that y equals 0. So that's why we end up with this negative value. It is not a physical position of the ball, but it is one that satisfies our mathematical equations. That's a good thing to keep in mind because it will help us understand why we get certain values and things like that from our equations later on. So for this problem, which time do we want? We don't want the negative one, we want the positive one. So we're going to take t equals positive 0.553 seconds. We can now go back to the x motion and stick it into either equation, any equation that we want, which is basically number 2 or number 3. We can use either of those to then solve for x. I'm going to choose the second equation, the third equation, and let's stick t in there. Okay, I'm going to get rid of this part here, and we'll do that. So using the third equation, we now have x equals x naught is 0, plus v naught x, which is 20 meters per second, times t, which we found to be 0.553 seconds, plus 1/2 ax, but we know ax is 0, so 0 times anything is going to be 0, so that whole term is 0. So all we have then is x is equal to 20 times 0.553. We notice that we have seconds in the numerator, seconds in the denominator. They cancel, leaving us with the units of meters. We multiply out and we get x is equal to 11.1 meters. And that is the final answer to our problem. How far will it travel horizontally when it hits the ground? 11.1 meters. Very, very good. Excellent. Let's try another one. Let's look at a very similar problem. Dr. Evil is going to throw this ball, but now not horizontally. How about at an angle of 30 degrees above the horizontal? So same initial speed, 20 meters per second, but now at 30 degrees above the horizontal. Well, I'm going to redraw this diagram and we'll get started. So the problem now is Dr. Evil throws a ball 30 degrees above the horizontal, but again still at 20 meters per second from an initial height of 1.50 meters. What's the first thing we do? Again, draw a diagram. So I've drawn our diagram here. We've got Dr. Evil from an initial height of 1.50 meters, but now the ball is being thrown upward. So what's happening? The only difference between the last problem, where the ball was thrown horizontally, and this one, now the ball is thrown upward at an angle. So what's different? The initial velocity. So what's it going to do? Qualitatively, what's the motion going to look like? Well, just think about it. You throw a ball upward at an angle, what's it going to do? It's going to start out by going up, but then it's going to arc downward. So this is going to go initially upward, but then it's going to arc downward before it hits the ground. All right. What do we do next? Write down the variables. Now, hopefully you can remember them all from the last problem. What I'd like you to do, this might seem silly, but what I'd like you to do is to say the variables with me. We're going to always say them in the same order, and hopefully that will get them stuck in our minds, so that whenever you have one of these problems, you'll be able to just rattle them off just like that very quickly. Okay, first, x values, the x variables first. What are they? X naught x, v naught x, vx, ax. X naught x, v naught x, vx, ax. What are the y values? The y variables? Same thing. Y naught y, v naught y, vy, ay, and what's the last one? T. There we go. Before we can write down our variables, the values for our variables, we need to choose a coordinate system. Where do we want to put our graph paper? Where do we want to put our origin? Well, again, let's choose the point directly below the initial position of the ball. Assuming to the right is positive. I've drawn the diagram so that the motion is actually that way. You can draw it any way you want. You can have the person throwing it that way, and you can actually choose your x-axis to go that way if you want. It doesn't matter. I'll typically draw it this way so that I can draw my x-axis positive to the right, which is just the way we're usually we're accustomed to thinking about the x-axis. X-axis positive to the right, y-axis positive up, but you can define it any way you want. So I'll choose my origin to be directly below the initial position of the ball. So my axes then look like this. Here's x, that's y, x, there we go. So x and y. Now, what are our variables? Again, initial position is here. Here's the initial position. Final position over here. So x naught, y naught. What are the initial coordinates of the object? Well, the x value, x naught, is again 0. Y naught is 1.50 meters. So just like it was last time. 0, 1.50 meters. What about x and y? The positions of the final point. Well, again, it's on the ground, so that's on the x-axis, and the y value for anything on the x-axis is 0, so we know that y is 0. What about x? Well, x, that's the distance from the origin. We do not know that. So, and actually, how far will it travel horizontally? That's what we're looking for. So, once again, x is what we're looking for. V naught x, v naught y, the x and y components of the initial velocity. Well, now our initial velocity is at an angle of 30 degrees from the horizontal with a magnitude of 20 meters per second. We've got to break this down so that this side is v naught x and this side is v naught y. So what are those? What are the x and y components? Well, remember, from trigonometry, we know the x component, in this case, is adjacent to the angle. So that's going to be 20 meters per second cosine 30 degrees. So, v naught x, 20 meters per second cosine 30 degrees. Well, v naught y, that's the side opposite the 30 degrees. So that's going to be the magnitude, the hypotenuse, times sine of 30 degrees. So v naught y is 20 meters per second sine 30 degrees. There we go. Excellent. Well, multiply that out, and what do we get? We get that v naught x is 17.3 meters per second. V naught y is 10.0 meters per second. So we can fill those in for our variables. V naught x, 17.3 meters per second. V naught y, 10 meters per second. There we go. Excellent. Now, what about Vx and Vy? Well, those are the components of the final velocity, which is how it's moving over here. What's it doing over here? Well, we can see that it's coming down like that, but we don't know what the components are. We'll leave those blank. Ax, Ay, again, what is the acceleration? The acceleration is the acceleration due to gravity, which is always straight down. What are the components of a vector that points straight down? Again, remember, the y-axis is positive upward. We chose our y-axis to be positive up. In that case, a vector pointing down must have a negative component. That's why a sub y is negative. We've chosen positive to be upward, so downward must be negative. And what's the magnitude? 9.80 meters per second squared. So we know a sub y negative 9.80 meters per second squared. If we had chosen our y-axis to point down, then the acceleration would be positive, because it would be in the direction of the positive direction. But we chose positive upwards, so a sub y is negative. A sub x, again, the acceleration is straight down along the negative y direction, so a sub x is 0. Whoops, put this in blue. And t, do we know t? We don't. Okay. Well, there we go. Okay, very, very good. Those are all of our values. Well, you know what? We know a little bit more than we did last time. What can we say? What's v sub x? Remember, anytime a sub x is 0, the velocity in the x direction doesn't change. So what's v sub x? What is it? It's the same as v naught sub x. So we can actually just say, well, that's got to be 17.3 meters per second. Remember, that would come from the first equation in the x direction. All right, very good. So let's think about how are we going to solve this. Well, I'd like you to look at those equations again. What are we looking for? We're looking for how far it will travel horizontally. We're looking for x. Look at the equations. Is there any equation that has an x in it and you know everything else? Why don't you take a minute and do that? Okay? Did you take a minute and do that? All right. Well, what do you know? You know there isn't one. So how are we going to solve the problem? We're going to solve it the same way we did the last one. We're going to use the y motion to solve for t, and then once we have t, we can come back to the x motion and use the t to solve for x. So let's do that. And again, we're going to use that third y equation to solve for t, and then we'll use it to solve for x. So let's write that down. I'll write down that y equation, I'll put the values in and solve it, and then we'll find x.